Hey there, ready for another deep dive?
Always.
Today we're taking on algorithms.
Oh, a classic.
Yep.
By Robert Sedgewick and Kevin Wayne, right?
You got it.
Yeah.
It's known as like the ultimate guide to, well, making computers do incredible things.
Less about writing code, more about the thinking behind it, huh?
Exactly. Algorithms, data structures, the stuff that makes software actually smart.
I like that. Smart software. So, for someone who might not live and breathe code, why is this stuff important?
Because it's the invisible backbone of like almost everything digital. Physics simulations like how galaxies move,
Right, right.
molecular biology, mapping DNA, even architects
Yeah.
designing crazy detailed buildings on computers. It's all algorithm.
Okay, you've sold me on its importance, but this book uses Java, right?
It does, yeah.
Do I need to be a Java whiz to follow along?
Not at all.
Yeah.
Think of it like a chef showing you a recipe. You get the idea, even if you don't have their exact kitchen setup.
Ah, makes sense. So Java's just the tool, not the whole story.
Exactly.
So where do we even begin with a topic this huge?
Well, the book kicks off with strings. Seems basic, but super powerful. Think about it. Searching, sorting, even making data smaller for faster transfer.
Oh, I see. Strings as in, like, text, sequences of characters.
You got it. And the book dives into how to efficiently sort through them, find patterns.
Ah, pattern recognition, always a fun one.
Right. And there's even stuff on regular expressions, which honestly used to make my head spin.
Oh, tell me about it. Those things can look like a foreign language.
Totally. But once you get them, it's like a cheat code for manipulating text. The book breaks it down, why they're so essential, validating data, building search engines, all that.
Okay, strings, got it. But before we get all fancy with algorithms, what's the groundwork?
Chapter 1 starts with the fundamentals, primitive data types, integers, booleans, combining them into expressions and statements.
Ah, the grammar of programming, essentially.
Precisely. And then we move on to arrays, basically containers for storing collections of data. Like, imagine neatly labeled boxes holding information.
Okay, arrays, makes sense. Anything else we need at this stage?
This is where it gets interesting. The book highlights how even simple stuff, like dividing integers, it behaves differently on computers because of how numbers are represented digitally.
Oh, right, like when you divide 5 by 3 on a calculator and it rounds the result a bit.
Exactly. Tiny things.
Yeah.
But they have a big impact when you're building complex algorithms.
So, gotta understand how computers think, even at a basic level.
Absolutely. Then we get to build more complex structures.
Lead the way. What's next?
Data abstraction. All about simplifying complexity. Imagine a car engine, right?
Mm-hmm.
You don't need to know how every part works to drive.
Thank goodness for that.
Exactly. So data abstraction is like creating a black box. Hides the messy details.
You interact with it through these well-defined interfaces, right?
You got it. Don't need to understand all the inner workings, like using a steering wheel without knowing about gears and pistons.
Perfect analogy.
Yeah.
So it's all about breaking complex systems into smaller, more understandable pieces.
Precisely. The book uses a simple counterexample to show this. How abstraction makes code manageable, reusable.
Okay, that makes sense. And this leads us to managing collections of items.
You got it. Bags, queues, stacks.
Ah, yes, classic data types.
Right. Like a bag of marbles, just a collection. A queue, like a line at the store, first come, first served. And a stack, well, a pile of dishes, last in, first out.
Got it. Those analogies are helpful.
Glad to hear it. The book explores how to build these, using linked lists and arrays. What's cool is the same structure, like a linked list, can behave differently depending on the algorithm.
Wait, so the same structure can act like a stack or a queue?
Exactly. It all comes down to how you add and remove items.
Mind-blowing. So it's the rules, the algorithms that shape how the data structure behaves.
Exactly, like Lego bricks, right. You can build a castle or a spaceship with the same basic blocks.
Love that. Okay, bags, queues, stacks, what's next?
Efficiency. How fast our algorithms run. Chapter 4 dives into this, focusing on how running time changes as data grows.
So if I've got a ton of data, I need to make sure my algorithm can handle it without taking forever.
Exactly. The book uses the three-sum problem, finding groups of 3 numbers in a list that add up to 0.
Okay, I vaguely remember that one.
One way is brute force, checking every single combination.
Oh, sounds tedious.
Incredibly. But the book contrasts that with a more efficient algorithm, using sorting and searching tricks. It makes a huge difference.
So choosing the right algorithm is key. Got it. But there are tons of sorting algorithms. How do we even begin comparing them?
That's where Chapter 5 comes in. Sorting algorithms. Think of it like the foundation of a well-organized digital world.
Okay, love it.
And the book goes through a bunch. Insertion sort, selection sort, merge sort, quick sort.
Whoa, that's a lot of sorting.
It is. But the book does a fantastic job of showing, like, the strengths and weaknesses of each one. Like, quicksort, it's generally super fast, but can get bogged down in some cases.
Oh, interesting. So how do you avoid those quicksort slowdowns?
Randomization, like shuffling cards, keeps things mixed up, so quicksort runs smoothly.
Clever trick. So sorting, like most things in algorithms, is about using the right tool for the job.
You got it. What other tools do we have besides sorting?
Well, Chapter 6 introduces priority queues, all about, well, priorities. Imagine a to-do list where you always tackle the most urgent tasks first.
Okay, that's a relatable concept.
Right. The book explains how they're used in operating systems, making sure the most important stuff gets done first. And then it goes into implementing them using something called a binary heap.
Binary heap, another new term for the collection.
It's like, imagine a family tree, but the most important person is always at the top.
Ah, okay, so not just storing data, but structuring it so it's easy to find the most important stuff quickly.
Precisely. The book breaks down how you add and remove items from these heaps while keeping that all-important order.
Okay, priority queues, starting to get it now. A super efficient way to manage tasks based on how important they are.
Exactly. And they pop up all over the place. Network routing, simulations, all sorts of stuff.
It's amazing how it all connects.
It is. And as we go deeper into the book, we'll see even more of those connections, even more powerful algorithms.
Okay, I'm ready to keep learning. What's next?
Symbol tables. Essentially connecting pieces of information, like dictionaries. You look up a word, find its definition.
Seems pretty straightforward.
Concept is, but implementations can get wild. The book goes into all sorts of approaches, basic sequential search to more advanced techniques like binary search trees and even hash tables.
Okay, those last two sound intimidating.
Don't worry, we'll break them down. Binary search trees are like super organized phone books where you can quickly find a name. And hash tables, they use this clever trick with something called a hash function to like instantly access information.
Okay, I'm picturing like a super-powered index card system in my head.
That's the idea. Symbol tables, all about connecting keys with their values efficiently.
Got it. And they're used everywhere, right?
Yeah. Everywhere. Databases, compilers, search engines, you name it.
It's incredible how these data structures are like the foundation of so much.
They really are. And that brings us to the end of part 1 of our deep dives.
Whoa, we covered a ton. My brain feels like it just ran a marathon.
I hear you. But the good news is we've laid the groundwork. Ready for even more mind-blowing algorithms in parts 2 and 3.
Absolutely. Until then, everyone, happy computing.
Happy computing.
Mm.
Welcome back to our deep dive into algorithms. We're journeying on through Algorithms by Robert Sedgewick and Kevin Wayne.
My brain's still buzzing from part 1, but I'm ready for more. Where do we pick up?
Well, remember how we talked about analyzing algorithm performance, especially as data sets get bigger?
Right. Don't want our code slowing to a crawl when we're dealing with massive amounts of data.
Exactly. And that's where order of growth comes in. Helps us understand how an algorithm's running timescales as input grows.
Okay. Refresh my memory on that one. Important concept, but details are a bit fuzzy.
Think of it like planting a magical beanstalk. Some beanstalks grow at a steady pace, an inch a day. That's linear growth. But others might double in size every day, exponential growth.
Okay, I get the analogy. We want algorithms that grow more like the steady beanstalk. Right?
Exactly. Linear order of growth, running time, increases proportionally. Double the data, double the running time. But exponential order of growth, well, that's our out-of-control beanstalk, quickly becoming unmanageable.
So understanding order of growth helps us avoid those algorithmic beanstalk disasters.
Precisely. Chapter 7 gets into the nitty-gritty of analyzing sorting algorithms in terms of their order of growth.
Okay, sorting algorithms. We talked about those in part 1. How does the book approach measuring their performance?
It boils down to the fundamental operations. Compares and exchanges. Compares, the algorithm checks the order of 2 elements. Exchanges, it swaps their positions.
So, like counting the steps a dancer takes in a routine.
Love that visualization. Fewer compares and exchanges generally mean a faster, more efficient algorithm.
All right, let's test it out. What about insertion sort? How does it do in terms of performance?
Good example of quadratic order of growth. Easy to grasp, but gets slow as the dataset grows. Imagine sorting a deck of cards one by one. Works fine for a few, but tedious with the whole deck.
Like trying to build a skyscraper brick by brick, not very efficient.
Exactly. But for small datasets, insertion sort can be pretty efficient. Simple, straightforward.
So the right tool for the right job, as always.
Absolutely. Now compare that to mergesort, much more efficient for larger data sets.
Merge sort, that's the one where you divide the data, sort the chunks, and then merge everything back together.
You got it. That divide and conquer strategy is key to its logarithmic order of growth. Instead of brick by brick, you build prefabricated sections, then assemble those.
Okay, that's way faster, especially for a massive skyscraper.
Right. Merge sort, like a well-coordinated construction crew, breaks the problem down, combines the pieces efficiently.
So merge sort, the ultimate sorting champion.
It's up there. But there's a trade-off. Needs extra space to store those sorted chunks during merging.
Ah, so if you're working with limited memory, maybe not the best choice.
Right. That's where quicksort often comes in.
Quicksort, super popular, but I remember it being a bit tricky.
It is. Quicksort, like a master chess player, strategically picks a pivot element, then partitions the data around it.
So not just sorting blindly, but making smart decisions along the way.
Exactly. By partitioning effectively, quicksort can achieve very fast logarithmic order of growth in most cases.
Sounds impressive. But wasn't there a potential downside to quicksort?
Right. Like any brilliant strategist, sometimes quicksort can make a bad move, hits that worst-case scenario, slows down significantly.
So how do you avoid those quicksort blunders?
Randomization again. Randomly choosing the pivot element reduces the chances of those bad moves. Makes quicksort reliable for most sorting tasks.
All right, quicksort definitely goes in the algorithm toolbox.
Yeah.
Any other sorting contenders worth mentioning?
The book covers shell sort and heap sort too, but we can save those for another deep dive.
Agreed. My brain's already doing a sorting algorithm dance trying to keep up.
I hear you. Key takeaway. No single best sorting algorithm. It's about understanding the nuances, choosing the right tool for the job.
Okay, that makes sense. So sorting mastered, what's next?
Let's explore priority queues.
Priority queues, like those intelligent to-do lists. Always tackling the most urgent tasks first.
Exactly. Chapter 9 dives deep. Imagine a hospital emergency room. Patients triaged based on severity, making sure the most critical cases are treated first.
Powerful example. So priority queues are about managing items based on their priority, not just the order they were added.
Precisely. One common way to implement them is using a binary heap.
Okay, binary heap.
Like a binary tree.
You got it. Special kind of binary tree, highest priority item, always at the top, like the CEO of a company.
So not just storing the data, but structuring it so you can access the most important stuff quickly. Exactly. The book explains how these heaps work, adding new items, removing the top priority one efficiently, all while maintaining the heap's structure.
Okay, I'm seeing binary heaps, like a super efficient filing system for priorities.
They are. Used in all sorts of applications, task scheduling, finding the shortest path in a network, all kinds of things.
It's amazing how these data structures pop up in so many different areas.
It is, and we'll keep seeing these connections as we move forward.
Okay, excited to see where this journey takes us next?
Well, let's revisit symbol tables. Remember, they're all about associating keys with values, like a dictionary.
Right, starting to get a good grasp on symbol tables. Pretty straightforward, right?
The concept is, but the implementations can get complex. The book starts with a simple, unordered linked list, like searching through a messy pile of papers.
Okay, that doesn't sound very efficient, especially with a lot of papers.
Exactly. For larger data sets, we need more organized approaches, like binary search trees. Imagine a perfectly organized filing cabinet, everything in alphabetical order.
Much easier to search through.
Right. Binary search trees, you quickly find the key by repeatedly dividing the search space.
Like playing a game of higher or lower to find the right value.
Precisely. And then there are balanced search trees. Even more clever, they adjust their structure automatically to ensure efficient searching, even in worst-case scenarios.
So they're like self-organizing filing cabinets that prevent things from getting too messy.
Exactly. And then there are hash tables, completely different approach. They use a special function, a hash function, to map keys directly to their values in an array.
So like a magic code that tells you instantly where to find what you need.
That's a great way to put it. Hash tables can be incredibly fast for searching, but there are some things to consider, like handling collisions when multiple keys map to the same spot in the array.
Okay, I'm seeing the complexity of implementing symbol tables efficiently, more than just throwing data into a dictionary.
Definitely. But by understanding the trade-offs of each implementation, programmers can choose the best approach for their needs.
All right, symbol tables are making a lot more sense now. It's amazing how many different ways there are to organize and access information.
It is. And these data structures are fundamental, from databases to internet routing to compiler design.
Wow, it's all coming together.
Yeah.
Seeing these algorithms and data structures everywhere now.
That's the beauty of it. Once you grasp these concepts, you see how deeply they're woven into the digital world.
Okay, ready for the next chapter. What's next?
Now we enter the world of graphs, all about representing relationships between objects.
Graphs, you mean like those things with dots and lines?
Exactly. Chapter 11 dives into the details. Think of a social network. People are the vertices. Friendships are the edges connecting them. Or a map. Cities are the vertices. Roads are the edges.
Okay, starting to get it. Graphs are a visual way to represent connections.
Precisely. And once we have that representation, we can use algorithms to answer all sorts of questions, like what's the shortest path between two cities, or how to identify clusters of connected people in a social network.
Those sound like some really useful applications.
Yeah.
What are some of the algorithms used to analyze graphs?
The book covers a bunch, from depth-first search and breadth-first search, those are like systematically exploring a maze, to Dijkstra's algorithm, famous for finding the shortest path in a weighted graph. And there's Kruskal's algorithm, used to find the minimum spanning tree, which is like finding the most efficient way to connect a bunch of points.
Whoa, that's a lot of algorithms. Can we break those down a bit?
Of course, depth-first search and breadth-first search, think of them like two different ways to explore a city. Depth first is venturing down one street as far as you can go before backtracking. Breadth first is checking out all the streets in a neighborhood before moving to the next.
Okay, got a sense of how those two differ. What about Dijkstra's algorithm? How does that work?
Dijkstra's algorithm, it's like having a GPS. It factors in the cost of traveling each edge, whether it's distance, time, or something else. Systematically explores the graph to find the path with the lowest total cost.
So if I wanted to find the fastest route from my house to the store, taking into account traffic and road closures, Dijkstra's algorithm could help me out.
Exactly. Then there's Kruskal's algorithm, like building a network of roads or cables in the most cost-effective way. Finds the minimum spanning tree, the subset of edges connecting all the points with the lowest total cost.
Okay, seeing how these graph algorithms can be used to solve real-world problems, this is fascinating stuff.
It is. And graphs, they're used everywhere. Social networks, transportation, computer networking, you name it.
This deep dive is really opening my eyes to the power of algorithms.
That's great to hear. And this is just the tip of the iceberg. There's so much more to explore.
Okay, ready for the next challenge? What's up next?
Well, let's dive into string algorithms, specifically designed to work with strings of characters.
Strings, as in like words and sentences.
Exactly. Strings are a fundamental data type, and Chapter 12 is all about the algorithms that help us work with them effectively.
Okay, what are some examples of string algorithms?
The book covers quite a few, including substring search, regular expression matching, and data compression.
Substring search. That sounds like looking for a needle in a haystack.
It can be. But there are clever algorithms like Knuth-Morris-Pratt and Boyer-Moore. They can find a specific substring within a larger string efficiently.
Okay, those sound like powerful tools. What about regular expression matching?
Regular expressions, they're patterns used to match specific sequences of characters. The book describes algorithms for efficiently matching these patterns.
So if I wanted to find all the email addresses in a document, a regular expression matching algorithm could do that.
Exactly. And data compression algorithms, they reduce the size of strings, making them easier to store and transmit.
Like zipping a file.
Exactly. Huffman coding, Lempel-Ziv-Welch, widely used for data compression.
Wow, string algorithms are incredibly useful. It's amazing how algorithms can be designed for specific data types.
It is. As we continue, we'll see how these play a crucial role in things like text processing, genomics, and data communication.
Okay, I'm ready for the next chapter. What's next?
Chapter 13, we revisit data compression, all about reducing the size of data files.
Right. Data compression is like magic, shrinking files without losing information.
It is pretty amazing, and this chapter really dives into the theory and practice behind it.
Okay, remind me of the key concepts of data compression.
One is entropy, a measure of information in a data source. High entropy, lots of randomness, unpredictability. Low entropy, more patterns, predictability.
So, like the difference between a random jumble of letters and a well-written sentence.
Exactly. Data compression algorithms aim to use that redundancy in data, the repeating patterns or symbols, to reduce its size.
So, like finding a shorthand for common phrases or ideas.
Good analogy. The book covers two main types, lossless and lossy.
Remember those from earlier. Lossless preserves all the original info. Lossy sacrifices some for higher compression.
Exactly. Think about zipping a file, that's lossless. You unzip it, get the same file back. Saving an image as a JPEG, that's lossy. Some info is discarded to make the file smaller.
Okay, those examples make sense. What are some specific lossless compression algorithms the book covers?
Two important ones are Huffman coding and Lumpel-Zivwelch. Huffman coding is like creating a code where frequent letters get shorter codes. Lumpel-Zivwelch is like finding and replacing repeating phrases in a text.
So both are finding patterns to represent data more efficiently.
Exactly. These algorithms are used everywhere: text, images, video, all sorts of data.
Wow, data compression is a key part of the digital world, shrinking those files without losing information.
It is really showcases the ingenuity of computer scientists.
Okay, before we wrap up this part, anything else about data compression we should know?
Important point. Choosing the right algorithm depends on the data and how much you want to compress it.
So no one size fits all.
Right. For example, Huffman coding is good for text. It's relatively simple and efficient. Lumpel-Zivwelch is better for data with repeating patterns.
Okay, makes sense. Starting to appreciate the nuances of data compression.
Excellent. That'll come in handy as we continue exploring algorithms.
This deep dive has been so insightful, learning so much about algorithms, how they work, what they can and can't do.
That's fantastic. And remember, algorithms is just one guide in this huge, constantly evolving world. There are countless others out there.
It's mind-blowing to think about all the complexity behind our digital world. Sorting emails, recommending movies, mapping the human genome. Algorithms are the engines driving it all.
They are. And the best part, this field is always changing. New discoveries and innovations are happening all the time. Keep exploring, keep learning. Who knows, maybe you'll create your own groundbreaking algorithm someday.
I definitely keep that in mind. This has been incredibly inspiring. Thanks for taking me on this journey.
It's been my pleasure. And remember, everyone, happy computing.
Welcome back for the final part of our algorithm adventure. We've covered sorting, searching, data structures, even dipped our toes into data compression.
That's right. And now, with Sedgewick and Wayne's algorithms as our guide, we're reaching the summit: computational complexity.
Okay, gotta admit, that sounds a bit intimidating. Is this where things get super abstract?
It gets deep, but think of it this way. Imagine planning a road trip. You wouldn't just start driving without considering the distance, right?
Definitely not. Gotta know how long it'll take, how much gas I need, maybe plan some stops.
Exactly. Computational complexity is like planning that road trip for algorithms, understanding the resources it needs, time, memory, and how those demands grow as the problem gets bigger.
So instead of miles and gallons, we're talking processing power and memory usage.
Precisely. It's about understanding how hard a problem really is and choosing the right algorithm to tackle it efficiently.
Okay, starting to see why this is important. But how do we actually measure how hard a problem is computationally?
Well, Chapter 14 introduces a classification system.
Yeah.
Groups problems into categories based on their complexity. One key category is P, which stands for polynomial time.
Polynomial time, what does that mean? Like in plain English?
Remember our road trip. If the travel time increases proportionally to the distance, say an hour for every 100 miles, that's like a polynomial relationship. In algorithms, problems in P are those where the running time can be expressed as a polynomial function of the input size.
Okay, so like a manageable road trip, even if it's a long one. What about problems that aren't so well behaved?
That's where NP comes in, non-deterministic polynomial time.
Non-deterministic. Now that definitely sounds more complex.
It is. Think of it like this. Someone tells you they solved a really hard puzzle, but they don't tell you how. You can easily check if their solution's right, but finding it yourself might take forever. That's NP problems. Verifying solutions is quick. Finding them efficiently, not so much.
So like having the answer key, but no idea how to solve the problems? Frustrating.
Exactly. And one of the most famous NP problems is the traveling salesman problem.
Oh yeah, I've heard of that one. Finding the shortest route to visit a bunch of cities, right?
You got it. Seems simple, but the number of possible routes explodes as you add more cities. Even with supercomputers, it could take years, centuries, maybe even longer to find the absolute best solution.
Wow, so some problems are just inherently hard no matter how clever our algorithms are.
That's right. And whether P equals NP, meaning if every problem whose solution can be checked quickly, can also be solved quickly, is a huge unsolved question in computer science.
So like asking if there's a shortcut to every puzzle, a master key to unlock all of the doors.
Exactly. And if P does equal NP, wow, it would change everything. Cryptography, optimization, artificial intelligence, like a new law of physics. Totally revolutionary.
Pretty profound stuff. So computational complexity isn't just about measuring performance, it's about the limits of what's possible.
Absolutely. A reminder that even with today's computers, there are still boundaries to what we can compute efficiently.
So what are some practical takeaways from this journey into complexity?
1, choose algorithms appropriate for the problem's size and complexity. Like you wouldn't bike across a continent, you wouldn't use a brute force algorithm for a nuanced problem.
Right, right. The right tool for the job, understanding what each tool can and can't do.
Exactly. And sometimes it's okay to settle for a good enough solution, not perfect, but practical and efficient. Like on a road trip, a slightly longer route might be better if it avoids traffic or bad roads.
Makes sense. Real world's all about trade-offs.
It is. That's where good algorithm design comes in. Understanding the problem, analyzing limitations, and choosing the best way to get the results you need.
This has been an amazing deep dive. I not only understand algorithms better, but I really appreciate their power and their limits.
I'm so glad to hear that. And remember, algorithms is just one guide in this huge, constantly changing field. Tons more to explore.
It's incredible how much unseen complexity powers our digital lives. Sorting emails, recommending movies, mapping the human genome. Algorithms are the engines driving it all forward.
They are. And the best part is, this field is constantly evolving, new discoveries and innovations all the time. So keep exploring, keep learning. Who knows, maybe you'll even come up with your own groundbreaking algorithm.
I'll keep that in mind. This deep dive has been truly inspiring. Thanks for being my guide in this amazing world.
It's been a pleasure. And everyone, happy computing.
Until next time on The Deep Dive.